My name's Chandler Carruth. I'm here to talk about some fun things that we're trying to do with compiler design. I know there's been a whole bunch of discussion of like Carbon and successor languages. You may be kind of fed up with that. You may want a little bit more C++. I promise I'm actually going to try and keep the Carbon parts of this to an absolute minimum. This is mostly talking about, here, let me do this while I'm talking. This is mostly going to be about how to build a compiler and some interesting things we think we can do building a compiler and that we're kind of experimenting with on Carbon. I'm going to mention that, and there's some interesting interactions, but there's also going to be a lot of C++ code. This is stuff that hopefully works with any kind of compiler design that you might want to have. Also, just so you know, there is a link here to the slides. I hope the slides are live. If they aren't, don't tell me now. Tell me later. We'll fix it. We also are going to have some live demo. There's a lot of flexibility. It's going to be a really informal kind of talk, so I'd love to have questions, love to have discussion anytime. Don't hesitate to interrupt me. I also have really bright lights here, and so if I don't see like a hand, like actually just start talking or say something or like wave or something, and I'll try and make sure I get to folks. All right, so with that, let's at least kick off kind of the start to this. We can't modernize compiler design without having something to modernize. We need traditional compiler design first. And what is traditional compiler design? Well, I don't know about other folks, but for me, it started with this book. How many folks had this book in the compilers class? Decent number of people. Part of me loves this book, maybe just for the cover. Other part of me is really frustrated by the book because it is really anchored on a traditional compiler design. But it was seminal, and the work done by these authors was really seminal in how we build compilers today. I don't expect everyone to necessarily have had a compilers class, though. I don't expect everyone to remember a compilers class if they've had it, so we're going to do a quick overview of kind of traditional compiler design to make sure we all kind of understand the baseline we're starting from. It also gives us all of the vocabulary and terminology we're going to need. We start off with the lexer. Lexing, or the lexer, is what moves from text into tokens, okay? This handles everything to do with text, from characters to encodings, Unicode, white space, comments, all kinds of very textual things, right? Generally, these are kind of regular languages. If you remember the kind of theory of different categories of languages implemented with finite automata. How many folks in their compiler class had a healthy dose of automata theory and such? Awesome, awesome. I both really enjoyed that and also like it went over my head a little bit. We're not going to talk a lot about automata theory, I hate to tell you. That is not my specialty. And what this is doing is it's kind of taking all these textual things, it's distilling them away and producing a nice encapsulated abstraction, keywords, punctuation, operators, identifiers, whatever your custom literals need to be. Things like string literals and numbers are all kind of handled at the lexical level because those all start from text, right? They don't start from a higher level construct. Next up, we have the parser. So the parser is what takes tokens and it turns them into an AST, or an abstract syntax tree, okay? This handles nesting, handles the structure of things, the relationship between tokens. Generally, these are built around context-free or sometimes context-sensitive languages as opposed to regular languages. They're often formalized with grammars or a form of push-down automata. Common grammar categories that you may have heard about or read about or you may see are LL, LLK, LR, LRK, LALR. There's GLR. There's a whole world of grammars that we're not going to really talk about. Loads of theory in this space. Just tons of theory in this space. But if you're not using a formal grammar, or if you're trying to do something a little bit special with your parser, very, very frequently compilers are implemented using a recursive descent parser. It's super, super common. It lets you do a lot of things that some of the other parser, specifically generated parsers, don't let you do. So it's pretty widespread. Question at the back, yes?
Can you tell for illustration where C++ falls into these categories?
Where does C++ fall into these categories? Well, right now I'm just building up the terminology. C++ is kind of a mess, right? So the lexer in C++ is incredibly complicated because it's not just lexing. It also has to do preprocessing. And the preprocessor in C++ and C is very complicated. For folks who think the preprocessor is a very simple thing, I encourage you to stick with that illusion and do not read the source code to a C++ compiler. It's terrifying. On the parsing side of things, C++ is so far from a kind of common grammar category, it's not even funny. You can't parse C++ with any of those things robustly. You can't parse C++ robustly, even with recursive descent parser. We're actually going to talk a little bit more about that later, though. Yes, JF?
Recursive descent or parser generator?
Either. It's not enough for C++, and we are going to get to that.
With your C++, which one's the best?
Which one's the best? Well, it depends on what you're trying to do. So parser generators are much easier to build. They can be faster, and they formally validate the grammar. A recursive descent parser has more flexibility. It typically is much better if you want to kind of recover after complex error situations or kind of try and give really good error messages. Recursive descent tends to just be a lot better. It has a little bit more context with which to diagnose errors.
You made it very sensible. Thank you.
Are you including parser combinators in the recursive descent bucket? Would you say that?
Am I including parser combinators in recursive descent? Absolutely. Parser combinators are a way to program a recursive descent parser. Is how I would break that down, and a very good one too.
I just want to make a small remark about C++. So if you A times B, it could be being B declared of type A, or it could be just a product A times B being thrown away. That's very hard to parse. And it could be more. Yes.
There was an
You
example.
need to know what A actually is. So you need to look up the declaration of A before you
Context-free
can parse
grammar.
it.
You need to look up names. It's actually even worse than that, but we're not going to go there yet. Just hang on. Okay, let's stick with traditional compiler design. Traditional compilers, for the record, can't build C++. But I actually love the questions. Please keep the questions going. So go ahead, Ben.
Are you drawing a hard line between parsing and lexing? Because
Traditionally, the compiler design did. And so yeah, at the moment I'm drawing a really hard line because I'm trying to give that starting point. All right. What's next? Semantic analysis. All right, so we've handled the text, we've added structure, now we have to add meaning. And that's what semantic analysis is all about. Typically it takes some AST and it turns it into a correct AST, or it gives you an error message. And if you're lucky, a very nice error message, and if you're unlucky, sometimes in C++, a very ugly error message. But like, this is what semantic analysis is doing. It's responsible for things like name resolution, type checking, validating all of the input program. Simple languages often have very little to do here. The grammar itself largely produces a correct AST for very simple languages. But as you get to more complex languages, you start to see more happening here to validate what are correct inputs, eventually to kind of transform and even expand the AST to represent the meaning of the program, because the original parsed AST won't have enough information in it. You can get implicit operations added in. With C++, you start to see really exciting things like instantiation, where you kind of template stamp out copies of the AST for different type parameters. You can have metaprogramming. And then, of course, the most complex languages, C++, the semantic analysis has feedback to the parser, which is why you can't just parse C++. You have to have the meaning attached to the program in order to even figure out the next thing to parse. This is always expected to be the last stage at which you detect errors in a program. Traditional compiler design, this is where you diagnose all of your errors. From here on out, it is the compiler's responsibility to produce a working program. Before this and up to this, it may be that you gave the compiler a bad input. Making sense? Next up, you have lowering. And so lowering takes this correct AST, and it's going to lower it into increasingly lower level representations. Maybe some IR or intermediate representations, maybe multiple of them, and then eventually machine code, something your computer can actually just run. I am focusing on ahead of time compilers. I'm not talking about interpreters or JITs. It's this whole other thing. Traditional compiler design was focused on ahead of time as well. And this handles modeling and optimizing the execution of the program on a machine. Not its meaning, but how it will execute. And that's an important distinction, because that means that we can start throwing away information here at a much greater rate than we can before this, because we no longer care what the intended meaning was. We only care what will actually occur when we go and run this program on a computer. A question over there on the left.
Yeah, you haven't mentioned the backend and front end. Where does this now?
I haven't mentioned the back end and the front end. I'm going to draw that line. It's on this edge of the slide.
Can you pithily describe what you mean by meaning?
What do I mean by meaning? The semantics, the behavior. What should the program do when it runs? What was the intent of the programmer in writing that software, right? And the interesting thing here is that this isn't as concerned with the holistic intent of the program or the abstract machine. This is concerned with the actual execution of the program on a real piece of hardware. And this shouldn't fail on a valid input. Generally speaking, we don't expect lowering to fail. Once we get here, we believe we have a correct input and nothing else fails. We just go out, we produce a binary that can run. And lowering tends to be its whole own system because there is a tremendous amount of logic in this. And in fact, the entire back end of a compiler in the traditional design is the lowering phases. The front end is responsible for that very first arrow from the AST to some IR, and then the back end takes over and runs it the rest of the way down. And so most of this is actually, we're going to mostly focus on the front end. I'm not going to spend a lot of time on LLVM or optimizations. That's not this talk. I can give other talks some other year, but this time we're going to focus on the front end. All right. So what really led to the particular architecture you see in these kinds of compilers? It's based on history, right? So a lot of this theory was formalized and kind of built on machines and on programming languages that existed, and prepare yourselves for this, half a century ago. Okay, really? You all are just inured to that? When I realized I had to write over 50 up there, I was very sad, okay? Maybe it's just me that's feeling old, that's fine. This was a long time ago. Like, we have an incredibly rich history here of computer science actually formalizing how we build compilers, how we build programs. Yes?
Compilers in Europe are 200 years old.
I'm sorry?
Compilers in Europe are 200 years old.
This particular branch of compiler theory. So all of the influences came from that time, and you can kind of see that. Semantic analysis and lowering were fairly straightforward. I mean, they were exciting because we could do them at all, but they were fairly straightforward. We were dealing with really simple languages, C, even simpler B, things that looked like macro assemblers. There was really minimal optimization. Register allocation didn't exist at the start of this and was new during this period of time, much less other optimizations. There were often no IRs at all. The backend would go directly from an AST to machine code. They were very different. It was a very different world. And a lot of the focus was really on Lexing parsing in these ASTs, because a lot of the pressure was, how do we make these simple languages more powerful and more expressive? How do we formalize all this theory? How do we handle the scale? Because the machines were very, very small and very, very low power compared to today, but the software was already getting quite large. And so this is where all of the focus was. And so let's try and actually diagram out how this is. And I'm terrible at diagrams. I apologize. I freely admit I caved a little bit, and I'm using ASCII art. But I think it'll communicate to this. So we start with the lexer, right? And then we feed the tokens out of the lexer into a parser. And we do a parse tree or an AST into the semantics, and then we complete it into this nice AST that we lower. This is kind of how I imagined the structure to work. Who all thinks this is how the compilers are structured? Got a few hands? A few hands. JF is just waving his hand because he's a troll. So this is not how they ended up being structured. Very rapidly, they actually evolved beyond this because they were very concerned about whether they could process large pieces of source code on very small machines. So instead, they moved to an incremental and lazy design. So let's talk about the incremental side first. Right? You would parse just one function at a time, right? Or even smaller granularity, and you'd hand that over to the semantic analysis layer. It would check that it was correct, do anything it needed to do to fix it up, and then would hand that function over to the lowering layer. And that lowering layer would go and it would emit executable code for that function. It would destroy all of that memory, collect all of that garbage, go all the way back to the parser and do another function. All the way through, right? One function by one function. Very, very incremental process. And this meant it never had to reason about the whole program. Right? Whole program was a scary thing because programs were too large to fit into memory, sometimes too large to fit onto a disk. And disks were a different kind of expensive at the time. And so this was really, really important. They also had an idea of making some parts of this lazy. So instead of the lexer kind of eagerly producing tokens for the parser would actually ask the lexer, like, oh, okay, I'm done parsing that other function. Could you give me another token? Thanks. I'm sorry? Just golf, okay. I'm done parsing, give me another token. They would try and see if it was finished and it could actually do another increment of function. No, okay, give me another token. And the Lex would kind of feed the token back in, right? I'm sorry?
Do you do this different?
Do I?
Do this different?
Well, there's a whole talk, okay? It's like, we're only 16 minutes. You're supposed to be asking questions about these slides, not the next slides. Okay. Okay, so this was the kind of architecture. Now this is really, really efficient and really economical when your source code is like the most difficult thing to wrangle in the world. And you are struggling to grapple with the complexity of the programming languages because they're brand new, right? And they've just been invented. Right? All of this came from this idea of locality, but it's not the locality that we actually think of today. And this actually led me astray. I'm being completely serious here. This is not like a false story. When I first got into compilers, I read about this design and how it was locality optimized. I was also working on the LLVM open source project, and they were all super interested in, locality-based optimization. I was like, oh, of course they're doing this the same way, having no idea that these two words were talking about two different kinds of locality entirely. This is about the locality of the parsed code. Right? This is about keeping a small piece of code in the compiler at a time and being very incremental with it. Right? One token, one AST node, one function, trying to stream things through as cheaply as possible. Right? And was rooted in the needs of the machines and the source code. Yes, question?
How did this kind of design handle, and maybe the answer is that the languages that they were using at the time just didn't really allow you to do this, but like if you had like a shared type or something that was required across multiple definitions of multiple functions, like if you're throwing out all the stuff from one function to the next, how does it handle that? Or is the answer that it did?
Great question. So who here knows what an elaborated type specifier is? Okay. So an elaborated type specifier in C++ is where you have a class C and you can put class in front of it. Now, if you go back through C, it used to be you had to do that with every single struct. And part of the reason why you had to do that is that you might not have the definition of the struct still around. So, yes, some cases they didn't handle it. In other cases, they would build up a side table that tried to have a very minimal representation. But it was actually a bit of both. The languages were trying to compensate and provide more local information with things like elaborated type specifiers being required. And the languages were just simpler. There was less to keep track of. We didn't have, I don't know, how many special member functions are we up to, Richard? 5? I don't know. Like every type has like a host of special member functions and all this other metadata attached to it.
You also didn't always declare your functions.
I'm sorry?
You also didn't always declare everything.
And you didn't declare everything, right? Like implicit declarations were a huge deal because now I don't have to parse a whole declaration. Why would I waste time parsing a declaration, storing a declaration in memory, and then parsing it when I can just infer it when I see it the first time? And so all of the things were really oriented around the constraints of the time. More questions? Thought I saw another hand. Okay. So this isn't great. While it talks about locality, it's definitely not the locality we think of for performance reasons on modern computers. And to make things worse, ASTs are kind of the pinnacle of a cache-hostile data structure. We have an incredibly sparse data structure, full of edges, all of them modeled by pointers, where to do anything you have to traverse that pointer into some random location in memory. It's just awful for modern computers to work with ASTs. Question?
Just to be clear, the locality we were just talking about is locality of source code.
Exactly.
And this is talking about cache compatibility.
Right, and that's the problem. Sorry, I should have made this even more clear. Right, like we had scare quotes around locality here, but the locality we actually want, the cache impact of this stuff is really exacerbated by ASTs. And a lot of people think that an AST is going to be kind of small, right? Like, I don't know, like we've got like a small function here. There's not a lot of code here, right? It's like a function, a for loop. What do you think, like 20 AST nodes? No. 100 AST nodes?
Include vectors like 1,000?
No, not the header, not the header file. We'll prune out the header file. Just this function. Just this function. None of the instantiations either. This isn't a trick like that. Do you think I can fit the AST for this onto the screen? Look, I tried, okay? So it's really small. It doesn't fit. It actually keeps going. We only got down to part of the return statement at the very bottom, I think. No, we didn't even get to the return. That last line is the result plus equals. And we haven't even finished the for loop or done the return statement here, right? ASTs are massive in modern source code because there's a tremendous amount of information here, right? There's implicit conversions. There's all kinds of things happening here. This whole for loop desugars into a much larger for loop construct. There's a ton of information here. Okay. Yes?
Some of this is like claim-specific representation, right? Like you don't have to represent the implicit conversions.
You don't have to represent the implicit conversions, but you do need to model them somehow, and that's going to take memory. I don't know how you model implicit conversions without putting them in an AST if you have an AST. This may be a different way of putting it. Because you actually have to have them there to type check the rest of the AST.
You can make really granular nodes that are real pain to work with.
You can make really granular nodes that are a real pain to work with. You could, in theory, do that.
Has a plus equal operator in it, and I don't need as much detail.
You could break orthogonality, right? Like you could break orthogonality, but I think that'll just make your nodes large instead of multitudinous. I don't know that that's going to be a win. I'm sorry?
You really need two passes when loading, so you need to have a presentation.
Maybe we need two passes, maybe not. Okay, so the question is, do you think this warrants a better approach? I mean, I came at this for thinking we need a better approach because I looked at this and yeah, what? Go ahead.
No, we don't need to have code, just go home by last night.
Okay, yeah. I mean, look, that's a much easier talk to give, I gotta say. I think we might need a better approach, but it's important to understand why we need a better approach. Like, why do we even care about this? And so I'm going to talk briefly about Carbon. I apologize in advance. I promise I'm going to try and get some C++ up here soon. So one of Carbon's goals is really fast compile times. This is a very long paragraph that says really fast compile times in a lot of words. There are a bunch of reasons why we care about really fast compile times, and it's not just the compiler. We use compilers in a bunch of places that aren't a normal looking compiler these days, right? We have edit, test, debug cycles. Developers are using IDEs and editors with code completion, with complex developer tools plugged into their editor. They're expecting interactive level performance here, right? And so we really think that like it is super, super important to have very, very fast compilation for Carbon so that we can hit all of these use cases. A lot of folks kind of expect us to just make compile times go away by scaling it with machines, right? DistCC and everything else. But that doesn't really work because for all of these other use cases, you actually need the speed to be interactive, right? There's actually a human sitting there waiting, typing, expecting a response back from you. And you can't very easily use your distributed compute to scale this if you have this in the critical path of an editor action. So we really need to focus on speed for this. And so the way we tried to kind of motivate ourselves to, rethink everything and reconsider how we design things was we set some challenges to ourselves. So we want to parse and lex Carbon code at some particular speed. We aim for 10 million lines of code per second parsing and lexing. We want to do semantic analysis and kind of all of the, like, confidently say, like, this is a correct program at 1 million lines of code a second, and lower to a binary at 0.1 million lines of code per second. Maybe. There's some caveats there. And now the hands go up. Okay. So I'm going to go from what I think was the first hand. Go ahead.
So when you say lines of code, like, can you translate that into like gigabytes per second or something?
Can I translate it to gigabytes per second? No, let's just start with lines, but like no like white space comments. Like this is like total lines, like just like raw lines.
So
80 column lines, sure. Very back.
I'm just curious, why did you pick these numbers in particular?
Picked a number out of a hat, to be completely honest. That's not quite true. That's not quite true. So the way we actually got to this is we looked at like what is kind of an interesting medium-sized piece of software, right? And interesting medium-sized piece of software for me, of course, I'm very biased here, is Clang and LLVM, and LLVM in particular. Where like it's like, you know, depending on how you configure it, it's like 2, maybe 5, 10 million lines of code. That's 10 million lines of code per second. And I was like, I'd like to be able to kind of like parse that, the whole code base of LLVM, in 1 second on one core of like a decent computer. I'd like to be able to like semantically analyze the whole code base in 10 seconds on one core, or in 1 second across if I can parallelize it across 10 cores. And I'd like to be able to generate a binary in 10 seconds. It really was that boring. Like I just kind of like looked at a code base, picked a size. And the thing is, we're not like, we're not going to stop optimizing things if we get to this number, right? Like, but it was a way to kind of challenge ourselves and like push ourselves a little bit. I got a couple more questions.
Did you have a target from I press a key to my squiggle lines update?
Do I have a target, like an actual latency target? The folks that work on the IDEs and on the tooling for the IDEs have very, very real targets for that. That wasn't what I fed into this, though. Yes?
I would assume that like more than 90% of tasks involve both parsing and semantic analysis and maybe not lowering.
Sure.
So why need the parser to be so much faster than semantic? Why not do it like a pipe?
Well, okay, so why do we need this? Because we actually don't think that a lot of things, like there are a lot of use cases that don't need semantic analysis. For example, formatting is one thing that only needs to parse. You can often get away without semantic analysis if you're just doing formatting. And it's also one of the most latency sensitive things. It's also it's really hard to do very localized or cache anything for formatting, and so you often have to do the whole file. And so that's why there's a little bit of utility in this. Also, to be blunt, because we think we can, we like each of these gets harder, and so that's the other reason to kind of scale the numbers down a bit. So one more hand.
Yeah, mine was kind of overlapping on your numbers here. Do you have a comparison against the current parser?
It's a great question. I'm gonna come back to that in a little bit. More heads. Hold on. So one thing that I do want to mention is I'm going to talk a little bit more about these numbers. So if you just have questions about the numbers, it may be worth kind of waiting a little bit to see. But I do want to say like the question of comparison is pretty interesting, and it's both better and worse than you might think. But we're gonna talk about that a little bit later. All right, go ahead.
It's common to have a completely different parser and Lexer for interactive development purposes because it needs to look at comparison.
Great question. Do we need like a totally different kind of compiler in Lexer?
Go ahead.
I'm sorry?
So ... question mark. Go ahead.
Yeah, I totally understand this. So we could do that, but we don't want to. We would prefer not to do that. So for example, for C++, we have done that. We cannot parse C++ fast enough to build Clang format. And so we have a whole separate parser that is used by Clang format. It's not quite a correct parser either. There are two factors there.
I was thinking more about the error tolerance use cases.
It's for this one, it's not about the error tolerance. There are two factors here. One of them is textual inclusions. And we don't want to have the dependencies resolved when we do formatting. And so we built a parser that is not quite accurate, but doesn't care about what headers it missed.
I mean, just really dumb cases like you just jammed on the keyboard on a certain line, the formatter shouldn't just fall over.
I mean, we don't want it to crash, but we don't care about like giving you a particularly great formatting there.
Okay.
At least Clang format is not especially error resilient there. It expects roughly well-formed code. If you misbalance your curly braces, you can get Clang format to do some just amazingly bad things.
That point there is especially frustrating. Like most existing compilers optimize for well-formed code.
Yes.
And like 90% of the time plus in the IDE, the code is not well-formed.
I couldn't agree more. Hang on to that thought. There's more to come. We have more hands. One hand at the very back.
Do these numbers take I/O into account or only processing?
Do they take?
I/O, input output.
These are great questions. Let's actually get a little bit more into the presentation because some of these are going to be answered, I think. All right, so let's think about what these numbers mean. Because for me, like I started off with this number, and it just sounded like a good number, and so I told the team, like, oh, you should go make the compiler this fast. They looked at me like I was, you know, a maniac and like kind of evil to them, and I was like, no, it's just an aspirational goal. It's okay. Then we started breaking it down. So this means that we have a budget of approximately 100 nanoseconds per line to lex and parse that line. And we have a budget of approximately 1 microsecond per line to do semantic analysis. Now, these are budgets. I do want to be very clear. This is an average, and I'm not doing any kind of like white space, any of that stuff. And so maybe we get like a free 2x from white space, and maybe a 3 or 4x from comments. I don't know. But like this is going to be really tricky. So let's think about these in terms of kind of your standard latency numbers. Folks know this, have seen this slide in a whole bunch of presentations, I'm sure. Right, so we have, right, like CPU cycle is, you know, fraction of a nanosecond because we have nice multi-gigahertz computers now. L1 references 1 nanosecond, all the rest of these. So what is the implication of these numbers with those budgets? Well, it means that we have about 200 to 300 cycles to lex and parse a line of code with, at best, like 500 instructions on a kind of nice modern processor. We're only going to get roughly 1 main memory access per line for lexing and parsing. We can't, and this means we can't allocate memory per token or line of tokens or almost anything else. Like every memory allocation is just like nope, you're over, game over, go home. So many approaches that you kind of naturally want to take don't actually fit into this. We have to use every single byte of every cache line access to have any hope of hitting the kind of like super aggressive numbers we'd like to see here. And so this is actually the realization we started from. And we didn't like go and try and like calibrate our numbers to make sure they're really accurate or do anything else. What we really did was we stepped back, like, what would we do if we were trying to solve the hard problem here, right? What would we look for? What design would we reach for? And there's a whole discipline that's kind of been playing in a very similar space. Yeah, that was the team, I think, not me, because I'm the person who thinks this is a great idea. Okay, so how are we going to do this? There's this whole discipline around data-oriented design that was specifically trying to address performance challenges like this, coming out of video games originally, but it's been applied all over the place, where you have very serious, very tight latency budgets. And so my kind of thinking was like, what would it look like to apply data-oriented design to compiler design? Like, what does the resulting compiler architecture even look like? It definitely doesn't look like a lazy incremental, lex on demand and incrementally parse thing with an AST. That is definitely not the thing. But what does this look like? So locality, so just a brief refresher on data-oriented design. A key part of this is that locality alone isn't a good model for modern hardware, right? Like locality is important, but that's not enough. We actually want to be thinking about the utilization of the cache and the memory bandwidth. All of the inputs we can hopefully expect are in memory, answering the I/O question from earlier. If you have a good operating system kernel, it's going to work really hard and make sure that like your source code gets cached in memory. You're not going to be like spinning a disk. Worst case, you have an SSD. This should be very close to memory and cache bandwidth bound. And we don't have any like super challenging, complicated computations here. We're not multiplying matrices or computing dot products. We're not, I don't know, computing Taylor series approximations or doing any of the other like mathematically difficult things that would slow us down. So all we've got to do is access memory really fast. And the way you access memory really fast is by accessing it as little as you can, right? And really thinking about how do you use every single byte that you're going to actually pull in. And so this means that the entire architecture is going to pivot from being kind of lazy and incremental and locality focused around the source code to instead being very simple and memory dense. Right? We're going to emphasize processing inputs near the memory bandwidth speed. We want the memory representation to be as dense as we can make it, ideally at a similar density to that input. How many folks here want to take a guess at the ratio between a serialized Clang AST and the source code that goes into it?
5 to 1.
5 to 1, 5 to 1. So like 5 megabyte source code, right? You're going to have what? 25 megabytes of, right? Closer to 50. Like we regularly see source code in the tens of megabytes produce ASTs that go up into the gigabytes. The ratio here is astronomical, and we really want to avoid that wherever we can. And even for very large inputs, we don't think there's any reason to add complexity to the eager approach, because we have really big computers with tons of memory now, right? Like we don't need to try and like work around those things. We just want to actually use the memory we need to as efficiently as possible. And like there's some arithmetic here, right? You got 10,000 lines of code, right? Maybe 40 bytes per line on average, like 80 character line. You don't use all 80 in all of the lines, right? This is going to easily fit into caches across a wide variety of hardware. Now, streaming through cache at memory bandwidth seems like a pretty acceptable speed to me, right? And so now we can just focus on like, how do we do that? How do we get all the code out of the way? How do we have kind of nice, tight processing? Questions so far? All right. So the core thing we need here is we need some data structures that we're going to use to kind of achieve this. And there's a core data structure pattern that we find really, really useful over and over again for kind of building a compiler in this way. We start with a primary homogeneous dense array packed with the most ubiquitous data that we're going to need to access. And we use, sorry?
I got a little bit confused. Is this going to be able to compile C++, or is this compiling Carbon?
Right now we're focused on compiling Carbon, but it's just a design for a compiler. Right? Most ubiquitous data that we need. We're going to use indexed access into this array. And indexed access is, I just think, such a beautiful thing here, because it's going to make your most important connections become adjacency instead of having to be stored with the representation in the data structure. Right? Adjacency is free in terms of storage. And we get to do that for at least one connection between all of our entities in our data structure. Then we have side arrays parallel to this for each kind of secondary piece of data we need that maybe has a different shape or a different layout that's not going to fit into this very dense homogeneous structure. We kind of connect these two with a compressed index because we're using indexed access. We don't need to use a whole 64 bits of pointer. We can use something much smaller. And we can build kind of flyweight API handles to wrap these and give us a nice API for interacting with the data structure. Right? And this pattern is something we see, it doesn't repeat literally, but we start here and then we adjust it to fit the particular problem, and it's been working really, really nicely for us. And this pattern may seem really similar, because this actually is incredibly similar to a pattern in a totally different discipline, high-performance computing, where one of the key things you do to kind of make things fast is you take an array of structs and you turn it into a struct of arrays. And so this is some kind of weird combination of turning a tree-based data structure system and a linked list-based data structure system into an array of structs, and then pivoting one step further into a struct of arrays. And because we started with linked and tree structures because of heterogeneity, it's even more important to move to a struct of arrays because that allows us to accommodate the heterogeneity of the data we access, because we have an array for the different kinds of data we need. Yes?
Do you want to comment on the more middle road approach, which would be using more aggressive allocation models in traditional?
Using more aggressive allocation models, like just optimizing the way you implement the traditional model.
Like these structures are packed because you use this allocator
yeah.
And that kind of stuff?
It's a great question. Like, should we look at that? And my response is that is how every major compiler I know of that has had significant compile time effort put into it ends up working. They start with this traditional architecture, and they basically optimize it in that way. Certainly, I know Clang is incredibly heavily optimized to try and mitigate the performance impact of this with very clever allocation strategies and other things. So that is something that's been really well explored, and so we're kind of trying to, can we go a much deeper level? Other questions? So advantages of this pattern, right? Already talked about some of this, right? Like you get a really dense thing. Almost every bit in that main array we can manage to use, and so we have very few wasted bits. When we're pulling this main array in from memory through the cache hierarchy, we're not pulling very many bits in that we didn't actually need. Differently shaped data is factored correctly, so we don't have wasted padding. We don't have any kind of wasted regions of memory there. We use a lot of enumerated states and bit packing to try and squeeze out any remaining space we can. And then there's this one other advantage that kind of caught me off guard. And that's that these indexed accesses, they don't just give you adjacency as a form of connection, which is really nice. They also make this much more friendly to modern processors. Because when you're using a tree structure and you want to get to the next node in the tree structure, you have to read its address out of the current node, and then you can go to it. But that makes it a dependent access, right? And that's going to serialize these in the processor. When you're doing index access, you can just increment your index, right? You don't have to read the current node, which means the processor can speculate really aggressively. You can actually have loops over this that are unrolled really aggressively in the processor automatically. If you want to see a whole talk about how CPUs use this for lots of fun and profit, gave a talk about loops and how they get executed in the processor at CppCon a few years ago. But this turns out to be really, really nice. We get both the adjacency to save a connection, and we get a much faster access pattern. Question?
Can I ask, how are you representing this tree? Do you use a kind of prefix, a police notation?
We're going to get to this. Hang on to it. All right. So let's look at how this manifests at every layer. But before we get to the tree, which is very interesting, yes, let's look at how we do data-oriented lexing. So lexing is super easy, it turns out, to fit in this model. It already fits. We just build a buffer of tokens, right? We make this kind of nice and dense. We have a side array for things like identifiers and string literals. Everything that's kind of big and weirdly shaped is in a side array. And then we have our token, which is actually just a flyweight index into our nice dense array. This is really straightforward. But there's an interesting thing that showed up here. One of the classic challenges that you hit in building a lexer for modern languages is representing source locations. Right? You want to be able to map things all the way back to the text they came from. Super important for giving good error messages. And this is an incredibly expensive operation in most compilers. For example, Clang, this is easily the most optimized part of the lexer. It's one of the most optimized parts of the compiler. It's an incredibly sensitive component to the performance of the compiler because this mapping is incredibly complex. And this is where the language actually does us a huge favor. If we can kind of influence the language design a little bit, we could have each token be a source location and have all of the information needed to recover the exact extent in the text of that token. But the only thing you need is you need to not have a preprocessor, right? You need to not do token pasting, you need to not do a few other things, and all of a sudden you can build the tokens in a way that they perfectly know where they are in the original source code. And so we kind of tweak the language to do this, right? We let tokens directly encode their location, right? We compute the location extents on demand, and now we have a single 32-bit token kind of flyweight identifier that gives us both the token itself, but also any source location information we might need. Question?
When you say you tweak the language itself, do you mean like change the syntax or change how like the specification works?
Change the syntax if we have to. It's fun to think about, like if you actually like can change the language, what can you do? Well, you can simplify things as low level as the lexer.
If the same line appears twice in two different places in the source code, it's two different tokens?
We just have two different tokens for this. Absolutely. So we tie the token to where we pulled it out of the source code. So if you do that, we have different representation, which we're probably going to need to anyways. And so it doesn't cost us very much. But that's actually a really good point. Sometimes we end up having to duplicate the tokens when maybe you could avoid duplication in another design. But by avoiding the duplication of the tokens, you would then have to create duplicate source locations, and you'd pay the cost already, right? And we've made the tokens so cheap, we don't need to even stress about this. We can just freely duplicate tokens, which is a pattern that's going to come back in the future. So another thing that was mentioned earlier, balanced limiters. This is a huge problem in parsing, particularly for incorrect code, where you've got like 14 open parens and curlies, you're typing in your IDE, you try to do code completion, and it's like, I don't know. Like I don't know what this source code is, I have no idea how to help you out, right? And this is particularly a problem when you don't use a parser designed for an IDE, but a parser designed to be part of a compiler. And so we wanted to think about this when we're looking at how to build Carbon's compiler, and how could we make a compiler that was really well suited to fit into an IDE to be very, very resilient. One of the big challenges is recovering from mismatched parentheses, mismatched curly braces, unbalanced delimiters of any kind. Recovering this in the parser is extremely challenging because you have to kind of backpatch your data structures. You don't have the structures you need to form a valid parse anymore. And the best hints you can have to what the correct thing to do are actually textual hints, like what your indentation is at. And that's typically something that you wouldn't expect a parser to have access to. And so we simplified the lexing enough at this point that we actually felt really comfortable adding some complexity to the lexer to handle balanced delimiters in the lexer itself, where we still have access to tokens, indent, lines. We can do any kind of recovery we want. And a really nice thing is it makes it trivial to synthesize the necessary tokens to rebalance everything and give the parser a kind of reliably balanced structure to the input.
You could switch to the Python model.
No, this is not the Python model.
You could use indentation.
We could switch to the Python model. I like curly braces. I like curly braces. We're going to stick with curlies.
Python also has parens.
Yes.
Yeah, can you just explain that to me? So like, they'll like have a stack, conceptually have a stack of delimiters that it's expecting and just throws them at the end of the.
Yeah. That's it. It literally just keeps track of like, well, like if it sees a closing delimiter, it's like, well, that's not possible. Like you just close a curly and I've got 3 open parens. I guess I'll add 3 closed parens and then I'll close the curly, right? Like that must be what's missing there. Yes?
So it's wrong.
Absolutely. It marks that those are errors.
Yeah.
Yeah. It leaves an error, but then it forms a nice structure. And so now you can kind of do much nicer recovery in the parser. All right, so let's actually look at some code. I think we've talked enough. So we're going to do some, we're going to briefly do some live code just to show you how this works. All right, so the first thing we want to do is how do we actually get our tokens? So I don't like writing a lot of source code, so Carbon uses a whole bunch of preprocessor tricks to try and stamp out code because I'm too lazy to type this out. And so there's a .def file inside of the lexer that basically just stamps out all the tokens. And like we even stamp out a bunch of tokens that we're not using yet because it's cheap, it's easy, like they're just errors if they show up, it's not a problem. So we have this whole macro system here. I don't know if folks have used X macros. These aren't traditional technical X macros, but they're a related technique where there's a general Carbon token macro if you want to observe all the tokens. If you just want symbols, there's a slightly different version, right, which includes a spelling. And we have all of our tokens here. We also have special handling because we're going to do balanced delimiters. We have special handling for opening group symbols and closing group symbols so that we actually track what those mean and how to rebalance them correctly. And then we, of course, have all of our keywords. And we're going to build this into something like an enum. But C++ enums, I got to tell you, I'm not a fan. I want more from my enums than C++ gives me. And so we have this code which kind of looks like it's building a class, but it's just completely full of macros. And these are using a little utility we built in Carbon to kind of take and build out an enum for us from this kind of nice def files. And so you see some magic here, and we'll look at how this magic works. But you also have a nice API. So we have nice methods like, is this a symbol or is it a grouping symbol, right? Is it opening and closing, right? Do we have keywords? Is this a symbol which has its own intrinsic size? Or is this one where we're going to have to compute the size on demand? All these kinds of things. To give you an idea of how we do this, I can briefly show you the kind of enum base. We have this enormous CRTP base class / macro system that basically builds a class that acts like an enum, but has nice APIs and has lots of nice features. You can go check all of this code out. This is just the code at the top of tree. I'm not going to try and read all this code. That would get way too boring. But let's look at one other thing. So this is the tokenized buffer, right? And so we just have a class which is all the whole tokenized buffer. And a token is just wraps up this comparable index base. So we have a dedicated class that provides all of the utility we need for these indexed arrays. Because we recognize this is a pattern we use over and over again, we've tried to really optimize how we do this. And so this token is just an index into our tokenized buffer. We also have a line And so the tokenization system actually remembers all of the line structure of the code so that we can give you nice line-oriented error messages and other things. We have our identifiers. Again, we're going to have we're just going to have an array of identifiers, and so this is our index into the identifier array. We have some iterators, a bunch of goop to kind of actually fill out the iterator. We have literals, so we have real literals, and literals, just like identifiers and strings, you have to model them separately. And here we represent the mantissa and the exponent, whether it's a decimal or some other kind of literal. All of the literal handling is actually in the lexer. Eventually, we'll get down to all of this. So here's the actual API. So they're kind of two parts of the API. One is the static factory function lex. This does all the lexing. We do it all up front, at once, one shot, no big deal. And it just produces this tokenized buffer, right? One go. And then we have the actual query API. And all of the API, right, the token, the line, none of those can actually have nice APIs on them because they're just indices into the tokenized buffer. So all of their APIs actually sit on the tokenized buffer, and they take these flyweights as a key that you pass into it so that you can access whatever piece of information. So you can figure out, what kind of token it is, if you have, what line was that token on, give me a line number if I'm going to print something, or a column number. You can get the exact text that makes up the token if you're printing it. You can get identifiers, all of the actual information you tend to get from here. And when this gets too cumbersome, we build a little wrapper that bundles up the tokenized buffer in the index and has a richer API on that. And you first get the wrapper, and then you go to use it. I think you can even see that, like, this is how you get a real literal value, right? You actually start with a token, you go to the tokenized buffer, you say, can you get me the real literal value for this token? And it actually packages everything up and gives it to you with a nice API. But this is ephemeral. This isn't, like, stored anywhere. This is just while you're using it.
So token is effectively a key into this array of ubiquitous items, which has an index into the secondary array with literals.
Yeah, exactly.
For those who might be confused, since I was at first until I realized, what are these combined symbols you have in your editor that, like, this arrow?
Oh gosh, thank you. Okay, yeah, sorry. I use a fancy font that draws hyphen greater than as a nice looking arrow. Like it's just a hyphen greater than, but then it like draws it as an arrow. Yeah, thank you, Daisy.
Same with earlier, there were like equals with a cross through it. Carbon's not defining that as a symbol.
This just fonts, just nice fonts. There's nothing that fancy going on. I wish I were that fancy with Unicode. Only JF can be that fancy with Unicode in his code.
So I think the audience was wondering if you had some Unicode packing
No. Sorry. Just a nice font. All right. I don't think I need to save that edit. Okay. Folks happy with Lexer code? In that case, let's keep moving because I want to get to some more fun things.
Do you use automata in the end?
Not yet. All right, let's talk about parsing because this is the most interesting part. And we're running a little bit behind. I love all the questions, though. I don't mind being behind. Questions are wonderful. OK, so how do we represent a tree? So representing a tree with this data structure is really, really annoying to think about. You have to have some linearization of the tree. And what I wanted was that the linearization of the tree happens to match kind of a really useful iteration order of that tree. Because we're going to get the adjacency effect for those edges, and we're going to get that parallel access with the index, it's really, really nice if whatever linearization we end up with is also a very useful traversal. Okay? And it turns out that the one that ends up being most useful is post-order traversal. And so we actually use a post-order linearization to form the tree.
Is post-order useful because it's an LR parser versus an LL parser?
Great question. This is actually a really interesting factoid of grammars. The idea is, like, is post-order what you need instead of pre-order because of the difference between LL and LR? And you're right. It's not about the grammar, it's about the language. You can't really parse infix operators with an LL grammar. It's not possible. Like, there's a deep theoretical reason you cannot do that. You need an LR grammar to handle infix operators because you actually have to defer things, find the infix, and then parse inside out. And that's how LR grammars work. LL doesn't have any mechanism for deferring things, and so you can't ever get to the infix side of the left-hand side of an operator. Because of that, a pre-order traversal is useless. You would actually have to build the post-order traversal and then put it back into pre-order in order to do this, because we have infix operators. And so yeah, for anything with like an infix kind of syntax, you'll always find that you end up building a post order or visiting in a post order at some point. And it's really nice that that's also the thing we want to consume it as. We also force a one-to-one correspondence with tokens, which is a little bit weird, but it gives us a bunch of advantages. I mean, there's a simple advantage. We get to just cheat on allocating, right? How do we minimize our allocations? We know after we've lexed it exactly how many parse tree nodes we're going to have to build, because it's the exact same number as tokens we lexed. So we only have to do kind of sliding memory allocation once during the lexing phase. The other nice thing is, when we have this one-to-one correspondence, we can have a single edge from a parse tree node to a token, and that's always sufficient to represent the source location. We don't need a range or a set of source locations or tokens for any parse tree node, because we can instead make sure the grammar actually produces those in a tree structure in the parse tree, and use a single token reference from each one. And so this ends up being really, really, really convenient to kind of make the parse tree very dense. Yes?
So earlier you said you don't know how to do like implicit conversions without representing them somehow in AST.
Yes.
And here you're forcing a one-to-one correspondence between tokens and...
Great question. I've been very carefully saying parse tree and not AST. This doesn't capture semantics. This is just the parser. Just a parser. All right, we also have another trick. We leverage introducers to actually arrange the particular tree structure so that a post-order traversal actually always visits an introducer before the interior of that part of the grammar node. And this is really, really, really convenient. It's so convenient that we're willing to add introducers that we forgot about to the grammar so that we have this very kind of perfect bracketing structure to the post-order traversal of the parse tree. Okay, so also as kind of an interesting different way of thinking about this, this is basically a stack machine for observing the parsed structure. And in fact, a bunch of the consumers of this, the way you kind of do the traversal is that you build a stack, and you do the traversal pushing and popping off the stack so that you have the entire stack of the tree, right? And you can kind of imagine the full tree kind of the stack sweeping across the parse tree as you traverse. Okay, but this is really hard to imagine. So we're going to visualize this really quick. All right, so we've got some carbon code at the top. We're going to lex into something like this, right? This is the tokenized buffer, right? We've got a bunch of tokens in this, nothing fancy. This one's really straightforward. All right, so how are we going to parse this? So let's spread these tokens out so you can kind of see all of the tokens line up in columns here, right? Just so it's a little bit easier to track. And here we have the first kind of sub-expression, like y plus 1 is a boring like infix sub-expression, right? We actually can represent x colon 9032 as a boring infix sub-expression. And then our whole variable declaration is the thing that connects these together. We start with the introducer keyword, then we have the first little subtree, an equals, another subtree, and then the terminal is also the root of this parse tree, which is the semicolon. Right? By having an introducer and a terminal, we have this nice bracketing construct. All right? But how do we actually think about the linearization? Well, let's look at what a post-order traversal of this would be. Right? We're going to start with var, then we go to x, I32 colon, because in post-order you got to visit all the children first. Then we do equals, because we're going to have a left to right kind of tie break here. We do y, 1, plus, and then semicolon. So if we want to arrange these into a linearization, let's just stretch this tree up, right? And this is actually the linearization we use. And so on the right-hand side, we have the parse tree that we're going to build, right? And we now just walk down the parse tree to observe the post-order traversal of a tree, right? And we store parallel to the actual, we have a token in the parse tree, and we have a little bit of extra metadata so that we understand the tree structure. Like we can basically build a tree structure out of this, and we have a linear walk to kind of do a post-order traversal. Make some sense?
So you've rebuilt forth.
A little bit. I mentioned like it is actually a stack machine. From a parsing perspective, it's very much a stack machine. All right, just trying to make sure this one sinks in. We can skip other things, but this is kind of important. All right.
Yeah, the two sides of the equality are not children of each other.
Yes, this is actually a great observation. So right, like the first one is var, sure. The last one is semicolon, but there's differences, right? You have x I32 colon and x colon I32. The left-hand side is the lexical order, but the lexical order isn't quite the post-order traversal, and so we do actually store a token index in each node of the parse tree. Basically store the kind of parse tree node, and we store the token index. I think we still store a subtree size so that we can recover a little bit more structure. There are a few pieces of information we store here, but it's very dense.
Are you able to build this as you parse, or do you need to like parse and then linearize?
Great question. Like, can we build this as we parse? Because it's post order, and because of the comment made earlier that we're trying to parse roughly an LR grammar, we happen to be able to build this as we can parse. And that's really, really valuable. If it weren't, it wouldn't be nearly as efficient.
You do know you're reinventing P code, right?
I'm sorry?
I said you do know you're reinventing P code, right?
Yeah.
Yeah. Okay. This is how compilers all work.
I'm sorry?
I said this is how Nicholas Vierk's compilers all work.
Yes. There's nothing is new under the sun. All right. Folks, happy with this? Okay. So what does this look like in code? I'm going to have to be a little bit brief here for time, I think. We can at least take a quick look at what this looks like. So our parse tree is going to have a lot of similarity to the Lexer, right? We have a parse tree. This is our kind of whole parse tree. We build it in one shot with a little factory function to just parse the thing. We give it our tokens, right? We give it something we can consume. We actually do some logging if we, for debugging if we need here. And we have some nice helper methods, like we do track whether we encounter errors, that kind of things. We know the size. And then we have some nice kind of iterators that allow us to walk this parse tree in post order, right? So we've built a whole post order iterator, and we kind of give you this nice range accessor so that you can like write super simple for loops to kind of walk over this in order. We do have some nice other things here. So if you give it a specific node, for example, you can start the post order walk from a particular node. And we have nice ways of reasoning about this. We can also walk through the children of a particular node. We store a little bit of extra metadata in the tree so that we can figure out how to scan through things and find children. We also allow you to find all of the roots. And then again, because these nodes are flyweights, the actual normal node API is on the parse tree itself. And so you just have a key of a node that you pass in as a parameter. Then you have all of the methods, whether it has an error, what kind is it, what token is it, how big is its subtree, so on and so on. Make some sense? And somewhere, if I scroll far enough, I can get to the actual like storage, but it's at the very, very bottom somewhere. We don't have enough time. All right. So how do we actually build this parse tree? We also need to have a parser. So we technically have a recursive descent parser, but you know, we started kind of fixing kind of long-standing frustrations we have with how compilers tend to be built. And recursive descent parsers have a really frustrating classic problem. Deep recursion can easily exhaust the call stack because you're recursing over the syntax that the user is giving you. The user's giving you a program, and you're recursing over that. And so they can just keep giving you bigger programs, and then you can run out of stack space. C++, Clang, most recursive descent parsers have this problem. Clang actually has a number of very exciting tricks to work around it, where it will actually kind of try to detect when it's about to run out of stack, and then fork a new thread with a fresh stack and like continue parsing to make sure that we never give you we never run out of stack in less than a full stack space worth of recursive descent. It's very confusing. This creates tons of problems for the library uses of a compiler, right? Because like you don't know how much of the caller's stack has already been consumed when they finally call out to the parser. And so we wanted to try and fix this. And so what we've done is we've created a dedicated stack data structure and turned kind of just done this traditional derecursive operation on the parser. Just turned it into a normal state machine with a stack. And I think, like, I at least kind of expected this to be a kind of awful and mechanical and painful thing that made the code unwieldy and horrible. And it's actually made the code cleaner and easier to read. I was like really delighted by this. We already have this kind of nice enum-based set of parse nodes, the same way we do with the tokens. It's really easy to write a switch over those. It's really easy to kind of build a very, very compact stack to actually track your state through here. And so this ends up being really clean and really, really fast. And now we don't have any of this like recursion limit problems. I would do more live tour, but we're starting to get a little low on time, and I want to make sure you all can ask questions. So we're gonna keep going here. So what about semantics? This one's just a real frustrating thing, right? The whole, as someone brought up, the whole problem with doing this parse tree this way is that there is no hope that we can kind of augment it to represent semantics, right? We've built something really, really efficient, really nice, but it only models parsing. And so we have to have some other approach for doing semantics. And so the idea that I'm kind of encouraging right now, this is still very, very early, but we're going to try and see if we can model semantics as a compiler IR rather than as an AST, right? Like just like a compiler IR that you might use for optimization, but instead of trying to model the execution behavior, we're actually going to model the semantics, the program level semantics, right? These are generally structured in kinds of blocks, got an order of execution. For runtime code, this is actually really great, right? This is exactly the structure we want to represent runtime code in. We're going to have blocks with an order of execution and like control flow edges between them, right? And so first we build that, then we can run some process over it to type check it and validate the semantics. And we have a very straightforward lowering into whatever the rest of our compiler's IRs look like LLVM's IR, for example. And we can map the rest of the semantic analysis into the IR space as well. Right, we have an idea of declaring a name can be an instruction, right? Declaring types can be instructions. And we have compile time evaluation to actually go through, understand these, and do anything necessary like type checking or propagating things. So type checking ends up looking like partial evaluation and constant propagation with the verification pass at the end. Template instantiation looks like partial specialization if you've read optimizer literature, right? We can actually map a whole bunch of the things we need to do in kind of doing semantic analysis into traditional operations and traditional patterns from optimizer design. And we have good designs for how to represent an IR in a data efficient way. We can use nice contiguous storage for this. We don't get a fully exploded tree structure. The result is interesting. It feels a little bit like a metaprogramming IR. Not like metaprogramming the way any human would ever want to use metaprogramming. Don't kind of read too much into this. It doesn't go all the way into the language. But it is, at some level, an imperative model for building each construct of the language. And then we build, on top of that imperative model, the kind of verification and type checking steps we need. We think this leads itself to really efficient patterns, things like interpreters and very efficient streaming data structures for compiler IRs exist, fairly well studied. I also have a hope that this is going to make it a little bit more straightforward to see how we implement really advanced metaprogramming features from the language, because we're already going to have an imperative model under the hood. It's too early to tell whether this works out well, and the model that this layer uses is almost certainly not the one you want to directly expose. It's not a nice or convenient model. It's this incredibly kind of meticulous and painstaking model. But it is still imperative, and I think that's really nice. Yeah?
So at which point do you do a name lookup? Because like
Here.
You do that on the ER.
Yeah.
I found that really annoying because like name lookup inherently has, like you have scopes of, like you have some tree structure there in the names. So how do you map those to the flat list of declarations with the flat list of instructions?
I mean, you can think of name lookup and name resolution very similar to use-def chains in an IR, right? And, where you're basically going and saying like, well, I have the set of names available, and you go and you reference a name. I look at the set that I have, I find one, and I attach it.
So you just sort of like iterate over the declaration scheme that should be like.
Yeah. Not in the tree, in the IR itself.
Yeah,
Like,
I mean, but like you iterate over it as if they were like unique.
Yeah. Yes.
How much of the LVM passes do you end up re-implementing with the different structures in it?
This is a great question. Are we going to end up re-implementing any LLVM passes? I mean, I hope not, but it's always possible. A lot of other programming languages end up with some semantic IR and implementing some amount of high-level language optimization passes at that level. But it's not clear we'll want to use this for that purpose anyways. For example, because we're going to be doing type checking and things like generics and templates at this layer, we're very likely to want this to be an immutable IR, which might be just really a bad fit for any kind of optimization, even high-level language optimizations. We haven't made it enough to be sure, but I think it's reasonably, like there's an even chance we're going to have to create a second IR for that if we need it. And that's where the duplication, I think, if we have any, will come up. Certainly that's a layer that Swift has had to duplicate things, Rust is duplicating things, other languages have had to duplicate things at those layers. Some languages are using MLIR to try and reuse common infrastructure. I don't know if that will work. But again, this is such a very different IR design, and it's not really solving any of those problems. It's solving an orthogonal set of problems. It's just kind of borrowing some ideas from IR. We don't expect to do a whole lot of optimization here. Yes?
As a general compiler design, does this put upper limits in terms of how far you could take type inference?
Does this place upper limits on how far we can take type inference? I don't know, actually. Maybe? I haven't thought about that. It doesn't come up because Carbon has very limited type inference. And so like, we haven't spent a lot of time thinking about that. I don't know if it does. That's kind of an interesting question.
Theoretically, if one would want to convert a file with this programming IR to, let's say, a C++ source code file, is that?
I'm not sure I follow what you mean.
Like, this IR seems like a stream of instructions in a very basic language, with definitions of functions, variables, etc. Try to convert to something that you can give later to plan.
I mean, we could probably kind of syntactically make it look like that, but it wouldn't have any meaning in C++ because there are things that don't have any meaning in C++ that we're going to represent here. Like there's no statement in C++ that corresponds to declaring a parameter of a function. But we have something very analogous to a statement that declares a parameter. But I actually would love to see a more kind of programming language rendering of semantics. I can do a live demo in a second, and you can see the current representation is very, it's a very faithful representation of the data structure in memory, and it's maybe not the most human optimized way of visualizing it. Jonathan.
So when you do name lookup on this ER, do you sort of like add additional information to the ER, or
Yes.
do you change the original representation?
Good question. Maybe. Here we go. So how do we build this semantics IR? I can come back and do a live demo if we want. So this is actually the primary driver of the parse tree design, because this is the primary consumer, right? We observe the parse structure, and we actually try to do basically a single pass over the parse tree and build the semantics IR in that pass. This is really difficult. There's some places where we defer it, but they mostly are things like nested function bodies, where we just defer the entire subtree of the parse tree. There's some intermediate data structures, but I don't remember if name lookup is an especially big one. I think there's at least a table of names that we do look up into.
So, like, do you have like an instruction that refers to a thing
Yeah.
by string, and then you change that to one that refers to it by index, or how do you handle that?
No, when we see the parse tree node, we build the semantic IR node with the index reference.
Oh, I guess because you're not like you have to put
Right. Yeah, we have the information we need when we get there. Right, and certainly, right, like single pass is going to get a little bit fuzzy when we get to template instantiations. There's nothing we can do though about that, right? Like this is just a fundamental challenge, and we're hopeful that it's going to be tolerable. Yes.
Yes. So just so to sum up, so you don't need to get rid like add back and modify or.
So one thing that makes this much simpler is that we get a lot of help from the language. So we're able to do a fairly kind of linear single pass over the parse tree and build a complete semantics IR in part because Carbon has a principle of information accumulation, which is that we actually introduce things before we reference them in the source code. And this means that when we're traversing the parse tree, we also see things before we need to access them, and we can kind of put together the data structures and get them all ready. By the time we need to access them, we can immediately look them up, get the whatever reference we need, and emit it correctly on the first try. So right now we have very little non-single pass structure. I think there might be a little bit, but it's very, very minimal. Yes?
And so one of the goals you stated at the beginning was so that it's easy to write things like a formatter and stuff like that.
Yes.
How toolable have you found it so far? Ignore the formatter, ignore the compiler.
Sure.
Like other tools that do cool things. How toolable has this been so far?
We don't know yet. It's way too early. Right? Like we're just writing this code. So like semantics IR has been in the works for a very, very short period of time. It's nowhere near done. I mean, the language is still getting implemented in all of this. So this is a very, 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 very early preview of where we're going. That is a question that I really look forward to finding out the answer to.
To me, the lack of toolability of C++ has only been not really a problem as much in the last 10 years. Before that, it was terrible.
It was terrible. We're gonna, if Carbon is successful, which remains a really big if, it is very much an experiment, but if it is, we're going to have to invest to like have all of the kind of tooling capabilities that we would need here. The hope is, of course, that we can build on top of this, but to a certain extent, the tools will arrive. Like that's not optional. We'll throw this out and redo it if we have to.
So you said you've had cases where you've modified the language to make
Yeah.
the parsing easier. Do you foresee a problem if there's some requirements, users want this thing, and there's no way you can shove it into the language without complicating your parser?
I mean, it is possible. It seems very improbable to me because the things that would complicate the parser are kind of weird syntactic sugar things. It's really hard to imagine like an expressive necessity that is also going to be impossible to do here. But it is possible, and like we can of course write like reach down and like say, well, here we got to do the weird thing, and like we're gonna like violate our invariants, and we're gonna like patch things up, or we can like change our design if we have to. But so far, it's actually been really. I've been surprised by how good it is. Speaking of which, I'm gonna just data oriented. We don't have a lot to talk about here because most of lowering is LLVM. That said, we are like the initial form of lowering. If we get semantics IR to work, then at least the initial part of lowering will be helped by that. Also, LLVM tends to be really, really inefficient. I did have a whole aside on testing the compiler that I'm sorry I'm going to skip. You can ask me questions about it later or check out the slides. So some key takeaways, because I have one thing that I want to do at the end. If you all want, I was going to actually show a little bit of live demo, because I haven't actually mentioned like a benchmark result. And there was a question earlier about whether it compares, and I feel like I should get back to that. But just like some key, very high-level takeaways while we've been doing this, just very early researchy kind of work on this, right? I really encourage people to rethink traditional compiler design, rethink traditional designs you run into. It's interesting to see what you can find there, right? Like go and look around and see if there's other ways of doing things. I love challenging assumptions with aggressive goals. Don't get hung up on the goals either, right? Like it's fine if the goal ends up being wrong, either not aggressive enough or like wildly unrealistic, but use this to kind of help yourself, step back from your assumptions and see what else you can do. And the last thing is that it's really nice to have compiler and implementation design as a major input to language design. Something I think C++ benefit a lot from is actually just thinking about, maybe humans don't care about the difference between one syntactic sugar and another, and one of them is a lot easier on the compiler. That should be relevant. I think that's actually a good piece of signal on which way to design the language. And it's one I think that we often miss out on with C++. It's something I would love to see more of. Yeah?
So you mentioned in this talk that the reality of computation hardware has changed the assumptions that go into these designs, and that's what's partly influenced you to try to do things out. Does that mean in 50 years we should expect a Carbon++ that redoes the way the language design is again, so that we have better...
It's just a compiler. I mean, maybe we'll have a Carbon compiler version too. But also, if Carbon succeeds, and succeeds for 50 years, I'll take it.
Like, comment about successor languages, is this just a bigger treadmill?
Sure. In some ways, I think it is. And if you actually go and read Carbon's, I don't want to talk too much about Carbon, but if you go read Carbon's like whole goals, there's a whole element about language evolution as part of the goal, to actually have language be able to evolve and change over time, specifically because this is a treadmill. Like there's no like a one-shot correct answer that we're going to find and then stick with forever. Right? Being able to change is actually the point.
It's more like a landfill because we never actually get rid of the other stuff. Just keeps going up.
Yeah. Anyways. So there's a bunch of future stuff if you want to check it out in the slides. I just want to kind of say, first off, thank you all, but I also want to try and do the brief benchmark live demo. We're going to see if the live demo actually works. So I made this like horrible script that generates Carbon, but it was a little bit tricky. Like I don't want people to get the wrong impression about what this actually looks like. It's the most boring thing ever. These are literally like a class and like a series of function declarations with like random strings generated for them. Because there's not a lot implemented right now. If I start getting fancier stuff, it stops working really well. But then if I go and I try and, no, that's the wrong one. Where's my benchmark? This is why you don't do live demo. Here we go. So if I go and I like run the compiler and I'm going to like take this giant thing, this is going to take a little bit of time. Just for the record, this is 10 million lines of code, right? Because I wanted us to parse. We don't have semantic analysis yet. This is just parsing, and I wanted to like measure in 10 million lines of code per second on parsing.
What are the system specs?
This is like I don't know, a modern Intel-ish server, like big server with tons of memory and a fast processor. And so you can see we're like at 5 seconds. We're not quite there. We're a bit too slow on an Intel machine. It's a little bit faster on my laptop than it is on the Intel server. So we still have some work. But the thing to keep in mind is we have spent 0 time optimizing this code. So we have a bunch of data structures that we think are quite nice. We spent no time actually optimizing the code. I took a quick look at the profile, and 1/3 of the time is spent in a hash table. I'm not too worried about like the optimization stuff here. This is very, very early stuff, but it's looking kind of nice. I also did actually build a C++ file as well. But again, I want to be clear, like it's not good code. It's not even really interesting code, right? This is just, because I wanted to try and keep it fair, I tried to keep things fairly similar between them. I think I did that in the other window. So this one, though, is a lot slower, but it's also a completely unfair measurement. I just want to be real. And so this is why like comparing to C++ is really hard, because this is doing semantic analysis on C++, right? It's doing a lot of semantic analysis. Eventually, this takes about 30 seconds. Anyways, a little bit under 30 seconds. And so Clang is not quite hitting my goal for the simplest possible C++, right? Classes with methods and parameters. Nothing else going on but classes and methods and parameters. Yeah, 27 seconds. It's pretty stable here. And so like this isn't quite hitting the goal, but Clang is ridiculously well optimized, right? Every technique that was mentioned about, careful allocation structuring, everything you can possibly do to minimize the locality hit from this, Clang does it all, right? Like it's had tremendous work trying to make this efficient, and it's still not quite where I want it for simple code. And I tried this like, so it was actually where I wanted. It was about 12 seconds when I didn't have parameters. And I added parameters to the functions, and it went to 30 seconds. And so if I add some more stuff to the code, it's going to get slower and slower and slower. And this is actually one of the scary things with Carbon. It's like if we add more stuff, it's going to get slower and slower and slower. But I tried both without and with the parameters, and it made no difference to the parse time for Carbon. Like I couldn't measure the difference in the parse time. And so it seems at least early on to be scaling a little bit better. No telling whether that's just because we have so much unoptimized code in the parser at this stage that like it doesn't matter. Well, time will tell how that plays out.
Could you put the flame graph of that in the chat maybe later, or we could like help us understand which part is the semantic analysis and versus.
Oh goodness.
It's a quick yes or no. You don't have
So I happen to have profiled Clang from my previous run of this, so I have it sitting around. And I can explain that that's a really hard question to answer. Because you see, no, I want the better one than that.
Were you asking about Clang, or?
I was just thinking like at time tracing, you dump it in flame graph, because maybe it's lying, maybe that's what you're trying to say, but it kind of breaks out a little bit.
Time trace isn't great, though. And the profile will show the same thing. I don't know if it'll finish fast enough. But if you look at the call graph, parsing and semantic analysis in Clang are interleaved, because it's parsing C++. And so like halfway through the parse, it has to call into semantic analysis to figure out how to do the next stage of the parse. And so it's really, really hard to tell which part is being slow. I know that the time report has a separation, but I don't really trust it. Here we go. So if I go and I look at like this, like, so this is clearly the parser, right? If we go and we expand it, we come in here, and all of a sudden we're in the semantic analysis part, right? And so like there's 10% of the time in the parser. Well, but no, actually like 7.3% of that time was in semantic analysis, not actually in the parser. And so teasing out where the time is allocated here is really, really difficult. It's especially difficult because like memory stalls and everything else, like really pinning down which part is responsible is hard. So I think ultimately we've got to get the semantic analysis of Carbon up to speed, then we can do a good comparison. And then we'll know whether this was really interesting or just kind of meh interesting. But I at least found like rethinking the compiler design interesting. Hopefully you all did as well. And there's tons of more resources and information. All this stuff is in the open source. It's all online if you want to. And thank you all so much. I think we have at least time for a little more questions. Question at the back.
I put the link to the slides in the Discord channel.
Awesome, yeah. I could also link to the slides if you want. Yes?
Do you think it would be possible, like considering the idea of data-oriented design and the linear traversal of trees, of breaking down the processing of the C++ code into more steps such that you don't have to keep going back and forth? That, like, for instance, things that can't be decided now be left as ambiguous nodes.
I mean,
like just keep doing that in more steps to avoid this back and forth and just have like more linearized trees.
I mean, so I'm not the best person to ask that. I've only touched Clang's parser intermittently. My impression is that that would be really hard. My impression is that it does do that sometimes, that it builds ASTs that aren't fully resolved and then resolves them later on. It certainly does that for like auto in a declaration, like it puts a placeholder into the AST and then later on it goes and it fills it in. We can ask, like Richard is around if you want to pick his brain on what could or couldn't be done in Clang. But personally, I'm not optimistic because I think a lot of the complexity you're seeing here is fundamental in the language. Like I don't think that they weren't trying to find better ways to separate things. Clang used to have a rigid separation between parser and semantic analysis before it supported C++. They broke that connection because they had to. And I suspect that most of the decisions there are forced on them from the language. Ben, go ahead.
Have you measured Circle or talked to Sean about its internal design?
Nope. It's closed source. I don't really want to know about the internal design.
So do you anticipate any, well, can you comment on the challenges that this new architecture might prove in the interop goals for Carbon and C++, given you're not using the same AST at all?
Yeah, sure. Interop is an interesting question. I think actually I'm not gonna like give a whole ton of that. Like, feel free to ask that at this keynote tomorrow, where I'm going to talk a lot about interop and Carbon. That's going to be a more Carbon-focused thing, but not really. I think we already like the challenges that it poses. We already are paying by having some separation. Once you have a separation, you have to map back and forth, and so we'll have to build a bridge. Jumping briefly back to the circle question, one thing I did want to point out. A lot, like this really isn't like completely novel. I'm not super familiar with verse compilers or P code, but like I'm extremely unsurprised that the whole like post-order linearization is a fairly common thing in lots of places. Like this should be done all over the place. I also know that Zig in particular, like very much in parallel while the Carbon toolchain was being written. The Zig compiler folks, I think, were also doing something extremely similar to this, basically trying to remove the tree-based data structures and switch to a heavily array-based implementation strategy. I wouldn't be surprised if Circle is also doing something like this. It'd be interesting to know. I don't think this is the only thing, and that's part of why I wanted to give the talk. It's like, it's not really that much about Carbon. It's really about having a more interesting compiler design. And I'd love to see more compilers try and try out really exciting and different designs. And maybe even this one is the wrong one, and we'll get another one that's even better, and that'd be awesome.
You mentioned Zig just made me wonder, are you interested in the other techniques Zig uses for optimization, like incorporating other parts of the toolchain you wouldn't traditionally incorporate and things like that?
Somewhat. I mean, we've definitely kind of been keeping an eye on Zig, and I'm super interested in what they're doing. I'm not sure all of it will make sense, but where it does, fantastic.
This is probably a very long-term question. Once it's time to bootstrap Carbon to have a compiler implemented in Carbon, do you expect to be able to migrate this code and all the effort you've been doing?
I mean, I hope so. I'm looking forward to the challenge that presents. I hope we just get to the point where that's an interesting question to ask. That would be the first thing. If we do get there, I do think it'll be really fun to see what it looks like to try and migrate code that looks like this. I saw a hand here. No?
Another modern compiler design that I've seen increasingly popular is dialing the incrementality to 11 and giving up on
Yes.
performance.
Yeah, so like making a super incremental or even an on-demand based compiler design is something that's really interesting. The Rust folks have been doing a bunch of work in this. There's this great blog post that from the folks who work on Rust Analyzer about the different kinds of design here. But one of the interesting things about Rust going towards an on-demand kind of maximally incremental design is that it was very much a response to the Rust language itself and the complexities they faced at actually getting really good low latency compiles, right? The things like proc macros and other parts of the Rust language make it very, very hard to kind of have a start at the beginning, run to the end compilation flow that's super, super fast. And they talk about in this blog post, they actually talk about how the ideal is not to be on demand. The ideal is for your language and your code to be so simple that you don't need to be on demand and you can just parse it at interactive speed. And that's really where we're aiming at with Carbon. We'd like to just see if we can keep everything simple and fast enough that we never need to have the on-demand thing. It doesn't mean we won't add it if it shows up and it's needed, but that's kind of the thing we're using as a kind of challenge to see how far we can push the design here. I'm sorry I don't have a link to that one handy. But if you hop on the Carbon Discord, I'm sorry? Yeah, fantastic. Someone's posting all the links for me. Thank you. Yes?
I'm assuming you are giving a similar answer, but the same question, but for raising your ASTs across different front-end passes. Like we do that in a clean tidy situation in certain cases for performance reasons, right? Mm-hmm. Does this design lend to something more to that, or have you I
mean, I don't know. We're not there yet, so I don't really know. My guess is that it'll work fine, but it also won't look anything like what's being done right now. Right, you're going to have some kind of semantic IR, and you're going to be reusing kind of chunks of semantic IR between passes. So I suspect that the design of the tooling will look very different as well. But hopefully, where there's kind of profitable reuse, we'll be able to do it. I don't know though. We're a long way from there.
I think my question was more because of the structure of your data, does it make it easier to save partial results and in a future pass just retrieve it from a cache somewhere?
I see. Kind of using cache results and kind of loading those.
I've seen that piece of a file before. I know it's the same. I'll just grab it from disk.
Okay, I understand better. In some ways, I think so, but I don't think the compiler design is the fundamental thing there. The thing that helps there is not having textual inclusion, frankly, right? Because if you don't have textual inclusion, then you have a built-in fantastic caching granularity for that purpose, right? You just do it per file basis. And certainly we hope that Carbon does that. We hope that future C++ does that with C++ modules. Like every language should be moving away from textual inclusion, because then you get that for free. Tony.
In terms of languages that are designed with the compiler in mind, D is probably one of them.
Yeah.
D very much started out as, oh my God, C++ is insane. You know, as a compiler writer, he just said, I give up and went somewhere else. So I don't know how, if the whole language kept going there, but I think it is.
I agree, yeah.
So do you handle include files?
Do we handle include files? Should come to the talk tomorrow morning. Sorry, that's more of a Carbon interrupt thing. I'm going to talk about that tomorrow. I don't want to spend too much time on that one. Awesome. Well, thank you all. We're already 5 minutes over, and I really appreciate it.